Hi everyone, I'm Abubakar Ango, and I am excited to be here today speaking with you all. This event is like a homecoming for me. I'm actually from Ilorin, Kwara State, Pakata area of Kwara State. So when I saw the CFP for this event, I was like, I definitely have to do this and be a part of the event. Now, so I'll be speaking about DevOps versus DevSecOps versus GitOps, ops everywhere. What exactly are all the ops about? Now, first, introductions. I'm a developer evangelism program manager at GitLab. Basically, that's a long form for just saying I enable developer advocates within my company to be able to work better and deliver more results. I'm based in The Hague, Netherlands, and my interests are in GitOps, DevSecOps, and Kubernetes. I'm a Google developer expert and a CNCF ambassador. You can always reach me on my website, abuango.me, or on Twitter at Sorki247. Now, let's go into the main topic. We all know Ada Lovelace. She wrote the first set of instructions that made computers to work the way they do. That's the first one, which was Charles Babbage's analytical machine. Well, I'm not sure we could call it computer then, but since it has some set of instructions, we can still call it computers. And since then, things have evolved. It's now hard to say a computing device is of a particular form. You know, previously we used to have Thor, we have desktop, we have this and that. Now, almost anything now can be a computing device. Okay, we have our desktops. We used to have our desktops, all those with all those cathode ray tube monitors. They evolved to flat screen. We have laptops, we had PDAs, we now have smartphones, we have iPads, watches. Almost everything now can be a computing device. Most of us are used to definitely our smartphones, are even more powerful than some of the powerful computers of the past. But now with the introduction of IoT, Internet of Things, almost anything around you can be a computing device. Your fridge, your shoe, your door, almost anything. And if we look at the past, when IBM, the former CEO of IBM then, was very short-sighted in his prediction of the future, he said, yeah, the world probably only has room for 5 computers. But look at it now. If we are just to look at computing computers that are like the main traditional computers we have, it's billions. When you now factor in the Internet of Things devices that are coming up now around the world, you know it goes into the tens, if not close to the hundreds of billions. Now, also, if you are conversant with networking, you will have been hearing things about IP addresses, Internet Protocol addresses, and we have version 4 and we have version 6. When version 4 was being created years ago, the creators of that protocol used 32 bits to form the IP addresses. And 32 bits will give you a total of 4 billion IP addresses for the world to use. They never envisaged to get to a point where almost anything around us will need access to the internet. We will need to have an IP address, which is why IPv6 was created. And now it's in the quintillions. I don't even know how many, because it's now 64-bit. It can take much more number of IP addresses. So that's to show you how the computing world has evolved. But all of this wouldn't be possible without software. We need instructions for how these things will run, for how they will communicate with themselves, for how they will interact with us to give us the result we want. For example, if you just shout to your home devices, hey, whatever device, okay, Google, what's the weather today? It will answer you and tell you the weather. How does it do all this? How does it recognize your voice, get all this understand exactly what you need, go online to fetch the right resources, and provide you an answer and speak it out. It's all through software. And that's where software engineering comes in. It's not enough for you to just write some bunch of code and you think you've created a software. There's a lot of process involved. There's a lot of planning involved. You need to carefully design the application you want to build. You need to carefully understand the requirements, the solution you're trying to solve before you create a software. And that is why we have things called software development lifecycle, the different stages in which a software is built. It starts with you having an idea. Oh, I want to create a software that will allow people to book refuse companies to come and pick refuse from a particular place. Okay, let's say your refuse dump is filled up and you want them to come and pick it up. You want to automate the process. You want to do like an Uber for garbage. An idea has to come first. You now have to think of, okay, what problem are you trying to solve? What solution? What suitable solution will fit that problem? What are the requirements you need? Then you have to sit down to design the different architecture. Those people that will use them, how will they interact with my software? How will they use it effectively? Before you even get to development. And as you are developing, you are testing. You are doing user experience to ensure that your users can actually use these devices, this solution you've created. Before it is now deployed, it's launched. And as people are using it, you are getting more information from them to change or to update the software, basically doing maintenance. So software goes through a life cycle, not just boom, go on your computer and you start writing some code. Now, there has been different approaches to this. One of which was the waterfall model. Waterfall model simply involves you having to talk to your stakeholders. Let's say you are the software developer. You will have to talk to your stakeholders, which can be maybe you yourself by doing your research and feasibility study, or if you are working within a company, probably your supervisors or the management of the company approaches you, oh, we want this. You gather as much information about the solution that you want to create. You gather as much resources. Then you do your analysis. Then you do your design, you do your construction. Everything follows one after the other from this stage to this stage to this stage to this stage to this stage. The problem with the waterfall model is it has to be one step at a time, and it's until one stage ends before the next stage starts. And that is a problem because as the software development world and as the world's changed, it's no longer feasible to have to wait for a stage to finish because requirements change by the day. Things evolve by the day. What you think might be a solution now might be stale or out of date tomorrow. And being able to evolve and make sure you are keeping whatever work you are doing up to date, that is why the Agile model was adopted. Agile involved you first starting with an MVP, a most viable product, or MVC. Sometimes it depends on the environment. MVP, most viable product, or MVC, most viable change. That's you just first start with something, then you keep iterating it, you keep shipping smaller changes to it, and it grows. You see, you are able to move fast, you are able to evolve as requirements change, and you are also able to keep up with new developments. And it doesn't just stop there. For Waterfall, it reaches an end where the project ends. Then if you want to do new things, you have to start again. But for here, the process continues. So it's usually, for Agile, most companies usually adopt what we call Scrum, where there are weekly or routine times where people come together, okay, analyze, discuss, share tasks to one another, execute the task, implement it. The next week they do the same thing. They keep shipping smaller iterations of the softwares. Now, but everything we'll be talking about are about just building the software, which running a software or running implementing an application is just beyond that. After you build the software, what happens? you need to deploy them, which is where this last stage of both of our models comes in. And this involves three things: developing the software actually, then operating the software, and ensuring that the software meets the necessary security, testing, quality governance, and a lot of other requirements, which is where quality assurance comes in. Now, the intersection of all these three is what we call DevOps. That's not just writing your code, but you need to be able to operate your code. You need to be able to monitor how the code is operating. That is where operations comes in. You need to be able to do what we call observability, monitor the application, and anytime there's an issue, you can respond quickly. You can iterate over the solution. You can push new updates or new patch. That is mostly done by the operations. And the different circles can be different teams within a company, or it can be an individual if you are just a one-man show. Now, but all this working together forms DevOps. Now, but DevOps isn't a tool or isn't just some model that you adopt. It's a culture shift completely, because it involves the whole organization thinking differently, adjusting the way they work to be able to collaborate with one another, have processes like the Agile process in place, and use the necessary technology to ensure that each development lifecycle evolves and moves from you doing your planning to you doing writing the code to testing the code to everything. Everything has to be an organization sitting down and deciding, okay, this is how we want to build our application. This is how we want to move, and this is how we want to deploy as fast as possible. Now, if we look at the difference between Agile and DevOps, Agile is simply like you moving from inception to launching and also reiterating. Before you launch, you keep reiterating over your application, adding more features, changing it, and so on. And as ideas come in, ideas change, you keep iterating before you finally launch. But with DevOps takes Agile and makes it a continuous process. You see that from the beginning, you build, you initiate, you plan, you build, then you test, you deploy, you operate it, you keep monitoring it. And as you are observing things and you are seeing things happening, you are moving back to planning and writing code, and continuously. It's a continuous process. It doesn't stop. Now, this gives rise to what we call continuous everything. That's where, in order to be able to keep up with competition, in order to be able to move fast afterwards, we all know that with the recent happenings in the world, there is more need to create solutions. There is more need to create tools. There's more need to ship out solutions to a lot of problems that we have. For example, now we have a lot of startups creating fintech solutions. They need to be able to move fast. They need to be able to create things as fast as possible. And this usually involves having a lot of developers working on the same thing and shipping changes as rapidly as possible. Now, but how do you then maintain, how do you keep up and test these applications and deploy them as they are shipped? That is where you have continuous everything. And continuous everything involves your developers are building, they are shipping. Continuous integration makes sure that, okay, as they are pushing all these their changes, everything is being checked to make sure they are pushing the right code, everything is fine, everything is going smoothly, and they are working based on requirements. And all these different changes they are pushing are being fused together to the main project. Then there's you've implemented some form of automation that will check in a number of things. Maybe you want to check some security implementation to make sure that your developers are following certain standard, or they are not pushing what we call dependencies, that certain parts that your application use from other places, they are not pushing wrong ones or unsecure ones or ones that your application, your organization doesn't support for certain reasons. Then there's continuous governance. You need to be able to check as your developers are pushing code daily or continuously. You need to be able to check that they are missing license compliance. They are meeting license compliance. They are meeting a lot of regulatory things that has been set. For example, PCI DSS is one of the regulations that most financial institutions need to implement to make sure that their application is secure. One of the things you can implement to check that every code that is being pushed meets that requirement. Then you also need to do continuous monitoring when your application has been shipped. Continuous monitoring to make sure that your application is running the way it should, and if there's any failure, you know on time and be able to fix those changes. Now, continuous deployment is where your application is deployed continuously. As new changes are being made, it's being pushed, it's being deployed immediately. You don't have to wait, or there are certain instances where we call it continuous delivery, where certain intervention is needed for the application to actually go live. This is usually done for when you actually want to go to production, because you won't want things to just, if there's a change that will cause problem and has passed all these other stages and gets to the production, but you didn't want it to go live yet, that is where you need to do what we call continuous delivery to make sure you review this change before it's actually delivered to production. Now, but for continuous deployment, you can use it in your staging or test environment where changes are deployed live automatically to your testing environment, and you'll be able to see it. Now, to achieve all of these, you need quite a lot of implementations, integrations, tools, and so on to ensure that your DevOps lifecycle keeps running as it should. As you can see from this slide, this is chaos, because that's a lot of applications you need to make sure work together, do things seamlessly, and as a company, you need to manage a lot of subscriptions. You need to manage a lot of resources and so on, and data moving up and down, which can pose security challenges sometimes, because everything needs to be communicating with one another. But that is where you have, in order to solve this kind of chaos, that's where you have DevOps platforms like the GitLab DevOps Platform, which encompasses all these different stages of your development lifecycle. That's from you initiating the idea, to managing it, to planning, to writing your code at Create, to verifying your code is fine and the way it should, to packaging it into either executable files or into images that can be deployed to your production, to making sure it's secure, deploying it, configuring everything within one platform. You see, you only have to manage one software instead of managing a whole bunch, which can be chaos. So you can look up what a DevOps platform is online and be able to learn more. So that means with a DevOps platform, the problem comes in, it goes through all the different life cycle, and the solution comes out without having a complicated infrastructure or setup in place. But if you look at this slide now, you will notice below there's secure and defend. DevOps focused more on, okay, how does the developers create their code? Like I said in the beginning, DevOps is a culture shift. It's interested in how does your application that you are writing get from the developer's machine to production. Every step necessary and procedure and planning necessary is what we call DevOps. But one of the problems with DevOps is it leaves security till the end, until something goes wrong, or until later they now go and meet security team, check this thing for us to make sure it's secure. That is where DevSecOps does things differently. Now, with DevSecOps, security shifts to the left. Left meaning things flow from left to right. Oh, you start coding, you start doing this up to production. But now, and then security. But now we are saying security should shift to the left, in the sense that right from the beginning, from you writing your application, from you pushing your application to your repository online, to you testing, security should be a part of it. When developers push their code, you should be able to test it through tools like static application security testing or dynamic application security testing to make sure that the application is secure, they are using the right tools, or they are using the right dependencies, or checking if, there are some times that you'll be writing your code and you put some credentials like the password or something you forget, or you put your environment variables within your code and push. Your DevSecOps system should be able to check and make sure that no credentials is pushed online. If your organization has some regulatory requirements, you should be able to check. So that's you ensuring that your security also becomes continuous, not just the development, the integration, and other. Security should become continuous. That is where DevOps becomes DevSecOps. That's security is part and parcel of the entire development lifecycle, not just at the end, where then you now call security team in. You can, most secure systems like the GitLab provides you with a security dashboard where you can see, okay, your security team can see, okay, so far, while doing the development of this application, these are the security vulnerabilities that have been discovered. These are some certain things based on certain industry standard that needs to be looked at. So as your developers are working and as your ops team are working, the security team is also having a live view of how things is happening, what vulnerabilities are happening, and they can be able to immediately, tap the security team. You need to do this. The development team, you need to fix this, or they need to set some certain requirements. So DevSecOps is basically security shifting left. If you are reading online or you see any industry thing and you hear shift left, it means that security is becoming part and parcel of the development lifecycle right from the beginning instead of the end. Now, let's see an example of a pipeline and at where security comes in. Now, if you look at on this slide in the verify box, you notice that when the developer from the beginning pushes their code, during continuous integration, it goes through checking things like code quality, performance testing, container scanning. Let's say you are using containers, and sometimes developers can use certain things that might not be secure, or some ports are being exposed unnecessarily. So scanning the containers to check for vulnerability is part of ensuring that your application is safe. And dependency scanning, yes, in software development, we depend on, we lift ourselves up on the shoulders of giants. That means you reuse some awesome distributable codes that have already been published by developers, which we call dependencies. But you cannot just be putting unnecessary dependency from anywhere, anyhow, into your code. You need to be able to make sure that you are getting the right dependencies and they are secure to use. And also sometimes, depending on the application you're building, there are certain licenses that you need to follow. For example, maybe your company does not use any open source dependency. Your CI pipeline, your DevOps pipeline, DevOps CI pipeline needs to be able to check to make sure you are following that rule. And so on and so forth. You need to make sure that everything that is going into your application is secure. Now, we also have things like static application security testing. We have dynamic application security testing. We have secret detection to make sure that no secrets or no credentials are pushed online as part of your code. Security credentials should never be added as part of an application, but it can be accessed. It should be designed in such a way that your application can access them when they need to, not that it goes as part of your application. Now let's digress a bit into an interesting topic called infrastructure as code, all this while we've been talking about how you build your application, how you build your software. But how do you handle what runs your software, which is your infrastructure? Previously, most times, if you want to deploy your application, you have to put it on maybe a floppy disk. In the olden days, to go put it inside your server floppy disk drive, drive A, copy it to the system and run it. Then we started using CDs. Then we now institutions also started having servers. But now we now have cloud providers. We have people like GCP, Google Cloud Platform, AWS Web Services. We have Azure. We have DigitalOcean. We have quite a number of them. Now, you can create a virtual machine to install things like Linux on it, Ubuntu Linux, to be able to run your application. Or you can go as far as Kubernetes to run a scalable deployment for your application. But how do you ensure that you have a structured approach to how you are creating your infrastructure within the cloud? And even if it is on-premise, maybe you have a fleet of servers, you need to be able to find a way to manage the resources of those servers as efficiently as possible and be able to have a history of how your infrastructure is changing, how resources are being deployed, who is using what, and be able to understand your infrastructure and how it has changed over time. That is where infrastructure as code comes in. So it's more like, instead of you physically handling hardware, you are now documenting it in code. That means you can simply write, okay, I need 4 servers to have, 1 gig of RAM each and to have like 10 gig of storage, but all of them should be able to communicate with one another within a network called a virtual private connection, and 3 out of them should have what we call a load balancer in front of it. That means they should be running the same thing, but there should be like a service in front of them that receives requests from outside and channels it between those servers. One of them should focus on being a database, and another of them should focus on being maybe like a DNS server, and so on. Now, once you define all of this in code and you use version control, we all know Git, to commit this into a repository, keep it there, save it there. And whenever there are changes, you simply make changes, and Git helps you keep different, all the updates that you are doing. It keeps it versioned for you so that you can be able to check different versions and understand how your code changes over time. Then you use continuous integration, like we saw earlier, your CI/CD, to now check, okay, this infrastructure this person has defined, okay, did they define it correctly? Are they specifying the right resources? Are they provisioning resources they don't need? Or they've over-provisioned resources, at the end of the day, they are costing the company money? You can be able to check that with CI. And with CD, continuous deployment, you can then push those your instructions on how your infrastructure should be to the cloud APIs. Okay, deploy, make sure this is how my infrastructure is. This is how I want everything to be connected together. Now, we use things, you can use a tool like Terraform. It helps you to declaratively define your application, your infrastructure, and push it online. And as you evolve, you can go and make changes to your infrastructure. And it makes sure that that thing you've defined, maybe later, 1 gig gram will not be enough. I need 5 gig gram for each of them. I need to add more servers. Infrastructure as code will ensure that once you commit this and push, it will go to your cloud provider and say, okay, let's change all this infrastructure. Let's add 4 gig RAM to them to make them 5 gig RAM. Let's add more storage according to how this person has defined. Now, but like I was saying, when you can use CI/CD, continuous integration and continuous deployment, with your infrastructure as code. But you need to be able to ensure that people don't just provision resources anyhow. And that is where merge requests come in. Because you're using Git already, or in GitHub they call it pull request, when you can have some form of authorization that is in place. When your developers have said, okay, this is what I need, then they submit a request. You then review it. CI will have run. You can configure it that CI should run. For example, if you're using Terraform, Terraform has what we call Terraform plan. Terraform plan, we go through what the person has defined and be able to give an overview that, okay, this person wants to create these resources and resources and resources in your infrastructure. This is how it will be created. It even has a feature where it will tell you this is how much it will cost. Probably you have a budget and you don't want to go beyond it. Then you can then review it in your merge request and say, but please review this thing. Or you make certain changes to it, or we don't allow this, or you are supposed to schedule them in this data center and not this data center before they are deployed. And this concept is one of the things where that is used for what we call GitOps. Now, in GitOps, you don't just declare your application just like that. You saw your infrastructure and deploy or your application and just it should also be in another place. And your application is later deployed to the infrastructure that you've defined. GitOps leverages the scalable infrastructure orchestration platform called Kubernetes. That's a big word. Now, let me explain. Kubernetes there was a time where the world started seeing that it is difficult to easily increase capacity of our servers up, and when there's demand, and when demand falls, for us to go down. Let's say, for example, when WAEC releases results, people hardly go to WAEC website, but as soon as WAEC release results, everybody wants to go and check. Then you see this website starts misbehaving. Using something like Kubernetes will be able to automatically create small units of your application that we call pods. And as soon as it notices that traffic has started increasing, it will now replicate those pods so that it can handle more traffic. And as soon as it notices that traffic has started going down, maybe everybody has checked their results, then it can be able to scale down automatically. Now, with GitOps, we have what we call the GitOps working group, which is like an organization, like a group of people that came up and said, okay, how do we define GitOps? And GitOps was defined as a set of principles. That means the way your application would be and would run and where it would run should be easily describable. For example, using like infrastructure as code. Okay, this is my application. This is how I think it should run. This is how I think it should scale when it sees load. And this is how I think it should scale when there's no load. That is what we mean by declarative desired state. That means you are stating that this is how I want my application to run. And this is what I want it to be doing. Then you've declared it, and you are also using, like infrastructure as code, you are using version control to push it into your Git repository that, okay, this is the state of my application and my infrastructure. Then using CI/CD, you do your checks, you do your testing, you do everything. Your GitOps strategy or pipeline should have a system where as soon as you push the changes to how you want your application to be and run, it automatically checks and go and check your infrastructure or your Kubernetes cluster. So now say, okay, how do we maintain the state of our application? Then it automatically implements the instructions that you've set. We have two concepts, your desired state and the actual running state. Your desired state is how you want your application to run, and the actual state is how it's actually running. So now your GitOps strategy, what we mean by continuous reconciliation of your operation is that anytime there are changes to your actual state, maybe an application is misbehaving or your infrastructure is just doing somehow, you should have some mechanism that will go and check your desired state. Did something change in my desired state? Even if something didn't change, let me go and check my desired state so that I can return my actual state back to how it's supposed to be. So that means your desired state is how you want it to be, and your actual state is how the infrastructure is actually running. So that your operations, the GitOps operations, ensures that your infrastructure and your application is actually running how you've desired it. Now, and this is done automatically. That is why we say it is continuous. Now, let me just show you a small, I think I'm running out of time, but let me just show you a small outline of how it works. Now, you see in our application repository here, as soon as you build your application, it goes through CI. Then your application is packaged into what we call a container and kept in an image registry. Your application is stored there. Then you've also defined how your infrastructure will be using infrastructure as code. That, okay, these are the resources I want to be deployed for the way my application will run. Then those information are stored in environment repository. Then we have within your environment, that means within your infrastructure, there's what we call an operator, GitOps operator, which will constantly keeps checking. That is, it will constantly be observing both the image registry and the environment repository to see if there are new things, if there are new changes in the way you've defined your application and environment. Then as soon as it sees it, it deploys it and ensures that, okay, it is how you've defined your infrastructure, that is how it's running. But if you look at inside the environment also, the operator also observes the deployment to ensure that it doesn't misbehave or go out of sync from how it should work. As soon as it does that, operator goes back to check the image registry and the environment repository to get the desired state of how the deployment is supposed to be and resets it back to how it should do. So it's more like it does factory reset to how it should be running if something goes wrong. Now, normally DevOps involves things moving from left to right, straight to your production, which is, that means your CI/CD pipeline pushes changes to production. But for GitOps, you can implement what we call a pull deployment, in the sense that there are some times or in some companies where your production environment is locked within a secure environment and your CI might be within another environment over the internet. So, but instead of requests to be coming into your secure environment like a bank, you want to restrict communication to the outside world. So pull deployment for GitOps usually involves, it is within your network that request is made and pulled in, not being sent to it. So it's one of the concepts that GitOps also use. Now, let me round up. Basically, everything I've been saying is DevOps is a culture that an organization adopts completely in how its people use technology through some process to achieve the solutions to problems they have. While DevSecOps involves applying security to DevOps, that means right from the beginning, you are ensuring that everything that is being done securely. And GitOps involves adding infrastructure as code and some more secure way to ensure that your application and your environment are deployed as they should and when they should, and also maintain your application as it should at every time. Thank you very much for joining me, and I hope I have empowered you with more knowledge in terms of how DevOps, DevSecOps, and GitOps relate to each other. Thank you very much.